Hi and welcome to this lesson on audio noise and spectrograms. Spectrograms are incredibly useful tools in sound processing. They show how the frequency content of a signal changes over time, making it easier to identify and isolate noise, understand speech patterns, and analyze the audio in detail. Spectrograms allow us to pinpoint the frequencies responsible for unwanted noise, remove them, and improve the quality of our audio files. But what exactly is this noise? Noise refers to any unwanted sound present in an audio recording and impacts the clarity and quality of the file. This includes sounds from the environment where the recording occurs, such as traffic, construction work, wind, birds, or people talking in the background. Other types of noise can include electrical noise from recording equipment, hum from power lines, or even random noise generated by digital processing. As you've probably heard, our audio file has intense background noise. Background noise can interfere with the audio content by masking critical frequencies and making it difficult to understand speech. Like humans, speech recognition systems also experience difficulties recognizing a noisy sound. Most tools have built-in noise reduction systems and are trained to handle such situations using audio, including noisy speech files. Noise in the audio file, however, can still hinder the accuracy of the transcript. So, how can we handle noise in the files manually? A good approach is to first visualize this noise and see its frequencies. Let's do so with our audio file in Jupyter and see where these hidden frequencies are. I'll copy the code I used earlier, paste it into a new cell, and execute it to obtain the file's waveform. Good. When we play the file, we notice that the first 1 or 2 seconds consist only of noise. My name is Ivan, and I am excited to have you as part of our learning community. On the waveform, this is visualized just before the speech begins, marked by a drastic change in the graph. We can identify the noise waveform by observing the amplitude of each sample. Furthermore, the file's last 1 or 2 seconds contains speech without noise.
IT and communications.
This is useful because it allows us to see the signal in this region and compare its graph to the rest of the audio, helping us identify which frequencies need to be removed. We mention frequencies quite often, but here we can see only amplitudes, right? So how can we use this information to obtain the dominant frequencies in the audio file? Well, this is where the short-time Fourier transform comes into play. Do you remember what it does? The short-time Fourier transform enables us to convert the representation of an audio signal from the time-amplitude domain to the frequency domain, allowing us to analyze the audio file's frequency components. This makes it possible to identify and reduce noise based on its frequency characteristics. Typically, speech recognition models perform this transformation internally as part of their processing pipeline, so we usually don't need to do it manually. But we'll demonstrate how to use STFT to visualize a spectrogram, an essential skill when working with audio data. Visualizing the spectrogram allows us to see the dominant frequencies and the frequencies of any noise we want to remove. We'll do that in the next lesson. See you there.